Okay, we're continuing our journey with AI basics. And you probably hate this by now because you've been hearing so many times about our journey where we started. We started with a dog and cat, simple classification work. And then we moved on to classifying bank transaction case, whether it's a fraudulent transaction or valid transaction. We looked at the confusion matrix. Remember the false positive, true positive, false negative, true negatives, that confusion matrix. And we also looked at the F1 score. The higher, the better, right? And then we classify it. Is this crop field healthy or unhealthy, right? It is either this or that, right? That's sort of predictions. And then diabetic patients who are likely to become diabetic. Is this diabetic or not, right? A or B, right? 0 or 1. That sort of classifications. And we also looked at the similarity heat map and similarity network with the bacterial samples. And we took mining companies, mineral ore samples, and document reports to calculate similarity scores. And we learned about scaling, right? Turning all the numbers into 0 and 1. And so that helped us calculate Euclidean distance and Manhattan distance, as well as cosine similarity. And then we learned KNN, right? Nearest neighbors, asking neighbors. We learned to use what K value has, what kind of effect on the outcome, right? K1 versus 3, 5, 7. If it is a binary classification, we want to use odd number, right? We learned that. And then we learned not only the minimum max 0, 1 scalar, but also we learned the standard scalar, which is the z-score. And then the problem with the minimum max 0, 1 scalar is that if there is any crazy outlier number, then it throws off the whole data. And so the z-scores standard scalar handles these exceptional outliers really well, right? So that's what we learned. And then we learned decision tree. Why do we use a decision tree? Because sometimes you need to explain why you have come to a particular result, so that decision tree turns a black box, which is very hard to explain. If somebody's loan applications got denied, you can't really explain it unless you know what sort of questions specifically were asked in what sequence, right? So decision tree turns black box into more explainable rationale. And then it makes the whole questioning process way more transparent. And then we learned about random forests, because if you ask one decision tree versus 100 trees, it's different, right? If you are having each of 100 trees to become independent decision maker, you get a very democratic voting as a result, right? So what's different is that if you ask one crazy tree, and the crazy tree or weird tree, then that answer may be really weird. But if you ask 100 of them, it introduces the diversity. And then independently, each tree makes a decision. And when you aggregate all the votes from 100 trees, that process itself is a very democratic process. So random tree is like asking a council of experts. And so it is a much more reliable. And then so we learned that you can achieve that through random forest. And then we learned about algorithmic bias. Biases that are introduced to an AI model, and then you looked at the few lines of codes that introduce the biases and which could happen from the data itself, or it could happen in terms of the algorithm that was developed. So what you need to do is do a 80% audit test, making sure each group of data points have a passing rate of 80%. So in the last example, the shift, night shift, day shift, the day shift were okay, but night shift did not make the 80% audit test, and the maintenance group did not make the 80%, where other groups like IT, admin, or HR and other personnel were fine. They passed 80%, but the maintenance group did not make them 80%. So there must be a bias, right? So that's how you know if the model is reliable or not. Now, today we're going to be introducing a whole new concept. So far, all the models that we looked at were like classified. Yes, no, or is either this or that or something else, like A, B, C, categorical data. So is this a fraudulent transaction or not? Is this person diabetic or not? Something like that. It's either this or that. And then we are going to have different kind of data as well. What if you want to predict, hey, how much is it going to be, like housing prices next year? Housing prices, we want to make some predictions. I don't know whether the housing prices will be higher or above certain number or below certain number. We want to be able to make predictions on continuous data, like hours. Will this last long or not? That's what the regression is for. And so with the regression, you can predict like someone's life expectancy. How long will this person live? If you have features like this person age belongs certain range, and then the health habit and the diabetic history or any other medical history. By taking considerations of multiple things, you would be able to make predictions on someone's health outcomes, especially with life expectancy. So, for example, if someone is smoking heavily, someone is drinking heavily all the time, and also under a constant stress all the time, and very old, what do you think? It's just easy to predict that that person's life expectancy will be shorter than other average people, right? So that's when you use regression. Now there are two types of regressions. One is a simple linear regression. So if you consider just one factor like drinking or smoking, obviously it would have effects on the life expectancy outcome, right? If it is a drone situation, in this case here, we're studying drone flight time, right? How long can this drone fly? Is it going to be 20 minutes, 40 minutes, 1 hour, 2 hours, depending on different factors? If you are just looking at one factor, for example, payload, and then weather, how cold is this? How high does it have to fly? If you're considering multiple factors, then it becomes a multiple regression. If you're looking at just one factor, it is a simple linear regression. So let's look at the codes and then see what can we learn about the regression series. So The first code, as you know by now, all imports, it's getting all the library to run the code here, NumPy, Pandas, Plotly, sklearn, and so those things. And then it prints basic things, and then it creates a random data set with 200 cases. Okay, and then we have factors like temperature, wind, payload, altitude, flight speed. Why do we need these features? So those who have played with the drones would know that if it is really freezing cold, the battery wouldn't last long, right? But if it's warm, the battery is okay. But if it is really cold, then the battery would not last long, and even if they are charged for the same period of time. The wind speed, if it has a tailwind or headwind, it's angled wind. If it is windy, the drone will suffer, right? And then because of the wind speed, the motor has to spin faster. The rotor will have to compensate for the loss of the flight. So wind speed definitely affects how long the drone can fly. And payload, if the drone is carrying some payload, is carrying 1 kilogram object or 10 kilogram object, it will definitely affect the flight time. Altitude, if the altitude is higher, obviously the air will be thinner and the motor will have to spin faster in order to compensate and then remain in the air. So the altitude matters. And then flight speed, if you want to fly at 60 kilometers an hour or 30 kilometers an hour or 10 kilometers an hour, it all depends. And so the speed also has effect on the overall flight time. So this is becoming quite important series of factors for drone company. If you're flying multiple drones to do a surveillance work, you do not want to lose the drone, right? You want all the drones to come back and be fully recharged and redeployed and so forth. You do not want to miscalculate the flight time and then you send the drone out too far and it just doesn't come back home to be recharged. Then you lost your drone, right? So if you're managing series of multiple drones, you want to make sure that you have a precise calculation with the minimum error so that they all come back home safely in one piece. So that first code is just creating the 200 flight data. And then the battery life range is 15 to 87 minutes, average battery life 46 minutes. And then if you look at the first 5 flight records, you see that there's a temperature, wind speed, payload, altitude, flight speed, and battery life. So it has a 200 rows of the data. So it created it. That's what the first block of code does. The second one, how does the feature affect battery life? Basically, with these multiple features, we want to see what sort of ranges we can get in terms of the flight time. And so here is the outcome one by one factor at a time. So the first one with red dots right here, if the temperature is minus 20, the flight time is much lower. But if the temperature is 40 degrees, then the flight time increases. So just the one factor alone has some effect, but not the entire effect, right? R square typically means that how much the variance is explained by this particular factor, temperature. So temperature explains about 23% of the outcome here. And so temperature certainly plays a role, but the not entire role of making impact on the flight time. So wind speed as well. Wind speed. If the wind speed is lower, it flies longer. If the wind speed is very high, especially with a headwind and then maybe side wind and other gust and other types of wind that is affecting the flight pathway, then obviously will make impact on the flight time. And so with that wind speed alone as a factor, it explains about 12% of the variance. Payload here, I think this is the most significant one, how heavy the object you're carrying. When I was traveling in China, I saw a hotel on top of a huge mountain, and they were washing all the linens and pillowcases and bed sheets and all those things at the hotel every day. And they could not carry them all down to the bottom of the mountain to wash them and bring all back up to the hotel on the top of the mountain by human labor, because it takes very long and the human labor is very expensive. So they were using drones to carrying the laundry from the top of the mountain to the bottom of the mountain, where they can comfortably and cost effectively wash them and dry them and then iron them and bring them back up. They were doing it all by drones. If they miscalculate, let's say there was a windy day, it was cold day, or you had to deal with flight speed, instead of going 20 kilometers per hour, maybe they had to go 60 kilometers per hour because they had to get the job done quicker or something like that. So it's a math. They do a lot of math to calculate the precise flight time, so that they will not lose a drone. They do not want to lose a drone in the middle of the flight, or if a drone gets an accident, that's very costly, right? If it crashes into a crowd of people, that is a huge accident. So they want to be very precise. So payload plays an important role in explaining the variance. In this case, payload itself as a one factor explains 34% of the variance. So that's much higher than temperature, which is 23%, wind 12%. Altitude 0.08%. I guess that's because I'm assuming this is meters, 100 meters, 200 meters, 300 meters. That is not very high altitude. If they are going up to 1 kilometer, then we're talking about some serious difference in terms of the battery time. But it's only a couple hundred meters, so the variance is not that much. And then the explanation, the R square, it's only 0.8%. So flight speed, how fast, the faster the battery will drain faster. But just like the altitude, it doesn't explain that much. It explains only 0.06. And so that is this graph. These graphs are showing one factor at a time. So if you're running a simple linear regression, that's what it is. Okay, so that's that. And then what if you put them all together? If you add them all together, you will have a much better explanation on the outcome. So if you put all together as a multiple factors, so that's a multiple regression, R square now is 83%. It's accurate. If you put certain factors together, so the wind, payload, and then altitude and speed, if you put them all together, you will have a pretty precise prediction how long the battery will fly. And then residuals here is errors, prediction errors. There is a majority of the errors fall from average 0 and then it goes down to minus 10 and plus 10, right? So it's important to understand the errors because all these things will have errors. It could have other factors that are playing in here. Maybe the battery, how old the battery was, that we don't know in here in this formula, right? But if the battery is older, obviously it will have a shorter lifetime. Maybe there was impact on the rotors of the drones. Maybe it has a little scratch on the rotors or something like that. There are other unexplainable factors that may play a role. And so in real world, there will be always errors. So you want to consider, how much error you need to count so that when you are making a flight, when you're planning a flight, you want to consider these errors so that, you want to be in the safe side. If you need to make a 40-minute flight, I would probably fly only 30 minutes, just in case. If the flight becomes shorter, then you're still safe. So that's when you need to know the errors. And here, how each feature affects battery life. If you want to know the details here, you will be able to see that payload makes the most impact on the battery life. And then so 1 unit change in the factor will have a 1 minute impact. So 1 unit with the payload, I guess it's a kilogram, then it will have 1 minute time difference here. The temperature, the warmer, the better, obviously. And then so that we understand the coefficient interpretation here, how many minutes of battery life change per 1 unit increase. So you can calculate, based on temperature, wind speed, payload, altitude, flight speed. So that's when you want to get down to the real precision numbers. So here it says that adding 1 kilogram payload costs 8 minutes of flight time. Okay, and then each 10 kilometers per hour of wind costs about 5.5 minutes. Flying 10 kilometers per hour faster costs about 3.1 minute less of a flight time. So having these details would really make proper plans, safe plans, when you flying your drones to do the job that you need in your particular industry. So that's what that is for. And then understanding R-square, what do these metrics really mean? Okay, let's look at the graph that this block of code generates here. Regression metrics explained. R-square is variance explained. Again, when you have all the multiple factors at play, and then it explains, all those factors explain 83.4% of the variance in flight time. So that's pretty high percentage. Like I said earlier, the battery, how old is the battery, or how old is the motor, how good the condition is of the rotors, whether it has scratches or not, whether they're all well balanced, all oiled properly, and so forth. So those are hidden factors that we don't know about. So that's why it doesn't say 100%. It doesn't explain 100%. It explains only 83.4%. How much of the variance does our model explain? 83.4%. That's good. Root mean square error. So that gives, this formula also gives a 7.18 minutes. Precise, very, very precise. What's the typical prediction error? Obviously, the lower the better, but we have a 7.18 minute buffer. So when you are making plans, flight plans, you definitely want to consider. And here it also calculates mean absolute error, which is 5.74 minutes. It's like, if the factors, all the numbers are entered, and then there's a little bit of a room of a 7.18 minutes root mean square error, but mean absolute error is, you definitely do not want to miscalculate by 5.74 minutes, because it means you will lose your drone in the middle of the mountain somewhere. So I would, as in real world, I would give a lot more buffer, and then I will probably give 15 minutes. I will double the root mean square error, like a 15 minutes buffer for the drone to come back home safely and be recharged and get redeployed. I do not want to use things like mean absolute error, 5.74 minutes. I would not consider that in the flight time and say, oh, I still have 5 more minutes according to the mean absolute error. I wouldn't do that, because there are other factors that are not explained. So we want to test if these features have these conditions, these data sets, then what would be the flight time? So it has different conditions for different missions, and then you need to make your own predictions, right? And then you get to see the results, right? And then you will run this final code, actual predicted battery life, and you get to see for each mission what will happen. So mission B gets the longest flight of 84 minutes. Why? Because it has only 1 kilogram payload, and then wind is calm, 5 kilometers per hour. Temperature is warm, 25 Celsius. And so it's pretty safe. Mission D, 53 minutes, second longest flight, 3 kilogram payload, and it reduces the flight time drastically. Mission C, for example, let's see, the weather is 5 degrees and then 40 kilometers per wind. That's very windy day. And then the payload is 4 kilograms. So if you compare that with the mission E, the condition, although it's minus 20 degrees, that's very cold, but the payload has 3.5 kilograms. So it's a lighter payload compared to the mission C. So remember how much each factor explains? We learned that payload has much more to do with the flight time than just the temperature of the atmosphere. So that's why, although it's minus 20 degrees, it's very cold, still it's much lighter payload. Therefore, it was able to fly 21 minutes. So, green is good. Green is good. Safe, if you consider the margin of error here between safe and caution. The red ones, definitely you are not going to make these missions because you're going to lose your drone. The green, you will not lose a drone. You will come back home safely. Yellow one, it's all right, but I would be a little nervous because it's closer to the caution line of 40 minutes. This gap here is the error that the model is giving us. So that's how you make precise flight plans with these models and then calculate your flight time properly. All the major airlines would do this all the time, calculating their fuel, payload, how many passengers, how many kilograms of or how many tons of the payload they will have in their airplane, and then the weather prediction. I mean, there are so many things they will have to plug in to get more precise data, and they still make a mistake. because they had more headwind than expected, or they miscalculated the number of passengers. I mean, that's a huge mistake. So in the aviation industry, these things are life and death. You do not want to make any mistake whatsoever. And so now you understand how important regression is in the world of machine learning and AI. So hopefully you picked up something interesting here, and we'll continue our journey with AI. Thank you for watching, and I'll see you in the next segment.